Let's start our next supplemental molecular model kit exercise. In the first part of this exercise, we're going to be going over the chair flip and showing a chair flip with a model kit. So first and foremost, here is our chair conformation. This directly matches the chair conformation that we have on the left. As we can see, if we look down the carbon-carbon bonds, all of the substituents are in the staggered conformation. Further, we have carbon 1 on the right pointing up, and carbon 1 on the left is pointing up, and carbon 4 on the right is pointing down. Additionally, I have the axial and equatorial substituents labeled. The axial substituents in red are pointing up, and the axial substituents in yellow are pointing down. The equatorial substituents, we have a set of equatorial substituents. The ones in blue are pointing up, while the ones in purple are pointing down. So as you can see, we have different types of axial and equatorial substituents. I'd like you to set up and make a cyclohexane ring. You don't have to use the colored atoms. I'm using the colored atoms to show what happens to your axial and equatorial substituents when the chair flip occurs. So we're going to be using this model and going through a chair flip. So in a chair flip, in terms of the basic idea, carbon 4 is going to get brought up, and then carbon 1 is going to get brought down. So net, what happens in a chair flip is carbon 4 gets brought up, and then carbon 1 gets brought down. That gives carbon 4 at the following position and carbon 1 at the following position post chair flip. Let's really try and showcase that. And to do that, we're going to go through each step of the chair flip using our model kit. Okay, so on the left, this carbon here that I'm touching, that is my carbon 1. On the right, this carbon is carbon 4. The first step in the chair flip, we're going to bring carbon 4 up. This makes what's known as the half chair conformation. As we can see, we have this pretty alarming eclipsing interaction between the substituents. If you trace down the ring, what you will see is that in the half chair conformation, you have these pretty destabilizing eclipsing interactions. So again, we brought carbon 4 up. This gives us our half chair conformation. To show you what conformation we are currently at, we are currently right here. This is our first step. That's where we're at. As we can see, carbon 1 is still up. Carbon 4 is now flat in the plane with the other carbon atoms. Now what we're going to do is we're going to bring carbon 4 further up. This gives us our twist boat conformation. As we can see, the reason why it's not a formal boat conformation is because we have these carbon-carbon bonds in the ring being twisted. The reason why the carbon-carbon bonds are twisted is we want to minimize this flagpole interaction. The next step is to bring our bonds in line. This gives the boat conformation. So in terms of the boat conformation, we are now right here. As you can see, the reason why the boat conformation is higher in energy is our flagpole substituents are adjacent, they bump into each other, and this leads to a flagpole interaction. Now, we brought carbon 4 up. We now need to bring carbon 1 down. So we're going to go to a twist boat conformation once again, and then we're going to push carbon 1 all the way into the plane of the page. And that in turn gives us our second half chair. As we can see, the difference in this half chair is now carbon 4 is the one that's puckered up. while carbon 1 is in the plane of the page. We still have these eclipsing interactions. So this gives us the half chair shown here. To finish off this chair flip, we are going to bring carbon 1 all the way down, and that in turn completes the chair flip. One thing that I would like you to notice now is that all of the equatorial substituents ended up in the axial position. All of the axial substituents in red and yellow ended up in the equatorial position. The other thing that I would like you to note is that if a substituent is pointing up, it remains pointing up out of the plane of the page. So let's show that. And this time I want you to pay very special attention to the blue and the red substituents. These are the substituents that are pointing up. Let's see what happens after the chair flip. So in this case, we're going to bring carbon 1 up. This gives us the half chair. We bring carbon 1 up again to get the twist boat. Next, we get the boat conformation. From here now, we're going to bring carbon 4 down. This in turn, let me get that all straightened out, gives us our half chair conformation. And from here, we push carbon 1 further down, and that in turn gives us our original chair conformation. What we can see almost immediately is that all of the equatorial substituents are now axial, but very importantly, all of the substituents that are pointing up remain pointing up during a chair flip. A chair flip only changes substituents from axial to equatorial position. It does not change the absolute configuration. So that's our first overview in terms of the chair flip. Let's now draw out what we've saw. Okay, so in this case, we started out with the set of axial and equatorial hydrogens. Let's just draw that out. Okay. We also have another set of axial hydrogens. And we have some equatorial hydrogens. Okay. The hydrogens in red and light blue are pointing up out of the plane of the page. They're pointing up, so they get a wedge. The hydrogens that are in yellow are pointing down. The hydrogens in purple are pointing down, so they get a dash. Let's go through the chair flip once again. So I'm going to label my carbons. This will be carbon 1. This will be carbon 4. Carbon 1 gets brought down. Carbon 4 gets brought up. And let's see what happens post chair flip. So I have carbon 1 and carbon 4. I'm going to bring carbon 1 up. Carbon 4 gets brought down. And that in turn completes the chair flip. As we can see, post chair flip, now if we draw out our molecule, draw out this chair conformation, we see all of the equatorial hydrogens are now axial, and all of the axial hydrogens are now equatorial. The hydrogens in light blue are axial up. The hydrogens in red are equatorial up. The hydrogens in yellow are equatorial down. The hydrogens in purple are axial down. So, key thing during a chair flip, all the axial substituents become equatorial, all the equatorial substituents become axial. However, the absolute configuration of each of your substituents doesn't change. The hydrogens in blue that were pointing up remain pointing up. The hydrogens in red pointing up remain pointing up. Okay, so let's talk a little bit about the chair flip. So in the chair flip, you'll label your carbons 1 and 4. Carbon 1 gets brought down, carbon 4 gets brought up. All of the axial substituents become equatorial. The equatorial substituents become axial. So let's practice using our model kit, drawing the chair conformation for the following cyclohexane ring after a ring flip. So first things first, I'm going to make a model. So I'd like you to pause the video at this time, go and make a model of this compound, and then we will discuss momentarily. So I'm going to be putting together a model of this compound, and it takes a little bit of time to put together a model because you have to make sure to swap all your atoms and that your atoms are in the correct spot in the ring. Nonetheless, we want to make sure to put together a model of this compound. And I'll be showing that model in the camera momentarily. You want to get comfortable making models of different compounds, including compounds drawn in Newman projection or chair projection, chair conformation forms, because it allows you to leverage what we've developed using our model kits. So the model kit is a very useful tool to help you understand each of these processes, understand chair flips and chair conformations. So it's important to develop and practice using a model kit. Okay, that prelude aside, here we go. So in this case, we have the following chair conformation. As we can see, carbon 1 is up, carbon 4 is down. Our hydroxyl group is pointing up in the axial position. The bromine is equatorial up. To give you a sense of what this looks like in a dash wedge model, this would look like the following compound. Let's do a ring flip now. Let's do a chair flip. So in this case, I'm going to bring carbon 4 all the way up, and I'm going to bring carbon 1 all the way down. I'm just going to check everything's staggered. It is. And here we go. We have our post chair flip, chair conformation. So in this case, if we're drawing what we see, the bromine is now axial up. The hydroxyl group is now equatorial up. As we can see, looking at our model kit, the bromine is axial up, the hydroxyl group is equatorial up. This is a key check to keep in mind because even post chair flip, the hydroxyl group in bromine's configuration is still up, still wedged. We've just, during the chair flip, changed from an axial to an equatorial position and from an equatorial position to an axial position. Wonderful. Let's keep going and let's do another example. So this time let's take a look at the following compound and let's show the chair flip for that compound. So let's go through and let's make a model. And then we'll discuss momentarily. So take a few moments, put together a model of this compound, and then we will go through and showcase the chair flip. So again, you want to just make sure that all of your substituents are in the right spots. So let's do a quick check now just to make sure. So here's the, oh. Okay, so here's our camera view. So let me orient this molecule in a way that makes it a little easier to see what's happening. So here, carbon 1 is on the right, pointing up. Carbon 1 is on the left, pointing up. Carbon 4 is on the right, pointing down. We have our ethyl group. We also have adjacent the chlorine. The chlorine is axial up. The ethyl group is equatorial up. And back on this carbon here, we have the bromine that's equatorial up. So as we can see, we've successfully prepared a model of this compound. Now let's do a chair flip. I'm going to bring this carbon up and bring my other carbon down. That in turn gives us the following chair flipped chair conformation. And as we can see in this case, the equatorial substituents are now axial. The bromine and ethyl group are now axial, and the chlorine is now equatorial. So let's draw what we see. In this case, if carbon 1 and carbon 4 is here, the ethyl group is now axial. The chlorine group is now equatorial. And the bromine group is now axial. So as you can see, it's really easy to see what happens post chair flip if you use a model. Let's talk about one more topic. Let's bring up one more topic as part of this discussion, which are cyclohexane Newman projections. So we can generate a Newman projection for cyclohexane looking down the C1, C2 bond. Let's make a model of this compound, and then we'll discuss momentarily. So take some time, put together a model of this structure, and then we will discuss. Okay, so let's do a quick check just to make sure everything is how it should be. So let's pull up the camera. So here in this case, we have carbon 1 and carbon 4. In this case, carbon 1 is down, carbon 4 is up. As we can see in this chair conformation, the ethyl group is, the bromine group in yellow is equatorial, and the methyl group in black is axial. The bromine is pointing equatorial up, the methyl group is axial down. Now, we can pick a set of bonds. So if we look down carbon 1 and 5, we can look down those bonds and in turn generate a Newman projection. So here's what the Newman projection view looks like. And as we can see, it directly maps onto the Newman projection view that we've drawn. The bromine is from the perspective looking at carbon 5, pointing up and to the left. The methylene group is pointing up and to the right. The hydrogen is pointing down. The back hydrogens are down and to the left and up. The back methylene is pointing down and to the right. Looking at carbon 1, the methyl group is pointing down, the methylene is up and to the left, the hydrogen is up and to the right. So as we can see, this view directly maps on to the Newman projection. We can also draw Newman projections post-chair flip. So for example, in this case, I'm going to bring carbon 1 up, carbon 4 down. That in turn swaps our substituents from axial to equatorial and equatorial to axial respectively. And now we can draw the same Newman projection looking down these same bonds. And this time, as we can see, if we do a comparison looking at the Newman projection post-chair flip, now the bromine is axial up, the methylene is pointing down and to the right, the methyl group is equatorial down, pointing down and to the right, and the methylene is pointing down and to the left. The back substituents, the hydrogens, are flipped from axial to equatorial, and the back methylene group is now pointing up and to the left and up and to the right, respectively. So as we can see, we can generate Newman projections for chair conformations by looking down instead of a single carbon, we pick a pair of carbons. So we're looking down carbon 1 and 5, and this is what yields the Newman projections. Okay, so let's try to apply that now. And let's draw the chair conformations for the following compound. And let's draw Newman projections for each chair conformation. And let's try to estimate which conformation is lower in energy. So take a few moments to make a model of this compound, and then we'll discuss momentarily. So first things first, we have to unpack a little bit what the dash wedge is implying. This methyl group has a wedge, so it's up. This hydroxyl has a dash, so it's down. So putting together a model for this, we can generate the following chair conformation. Missing a hydrogen here. Let me put the hydrogen atom onto this structure. Okay, perfect. So now in this case, the methyl group, we need one more hydrogen atom. Okay, there we go. Perfect. So in this case, the methyl group is equatorial up. The hydroxyl group is equatorial down. Okay, so now as we have our chair conformation view for this molecule, let's now draw what we see. So in this case, we have hydrogens on most of our other positions. The hydroxyl group is equatorial down, the methyl group is equatorial up, and we'll fill in the remainder with our hydrogens. Okay, everything maps out as it should. Let's now look down carbons 1 and 5. So we're drawing a Newman projection view. The most important carbon is this carbon 1 here. As we can see in the front, the methyl group is up and to the right, the methylene is up and to the left, and on the back carbon, the hydroxyl group is down and to the right, the methylene is down and to the left. So let's fill that in now. So we have our hydrogens. we have the methyl group up and to the right, the hydroxyl group down and to the left, and the methylenes are in the correct position. Take a moment, take a look at this model kit structure and compare it to the Newman projection that we've drawn. Okay, let's now do a chair flip. Carbon 1 gets brought up, carbon 4 gets brought down. That in turn flips our axial and equatorial substituents. And now as we see, both the methyl and hydroxyl group are axial. The methyl group is axial up, the hydroxyl group is axial down. The rest are just hydrogens, which aren't particularly important nor interesting. So as you can see, we are able to generate the chair conformation post-chair flip. Let's now look down carbons 1 and 5 once again. So here we go, looking down carbon 1 and 5, what we see changed is on this carbon, the methyl group is pointing up, the hydrogen is down and to the right, the methylene is down and to the left. On our back carbon, the alcohol is pointing down, and the back methylene group is up and to the left. The back hydrogen is up and to the right. So let's fill that in. Here we go. So let's just check to make sure we did that correctly. So here's our view of our Newman projection looking down carbons 1 and 5. And as we can see, it directly matches what we drew into the Newman projection template. This also highlights a really important point. When we say that this methyl group is suffering from a diaxial interaction, what it really is suffering from is a gauche interaction with this back methylene group. A 1,3 diaxial interaction, once again, is a type of gauche interaction. That's why they have the same energies. You can see that this methyl group and this methylene are gauche to one another. That's why this methyl group has a 1,3 diaxial interaction with this axial hydrogen and this axial hydrogen. So this is why we draw Newman projections, as it can really help us understand the nature of 1,3 diaxial interactions. So as we can see, looking at these structures, now to do some bookkeeping and tallying with regards to the energies. In this case, looking at the following structure, we have a methyl OH gauche interaction, which we would estimate to cost us about 2.1 kilojoules of strain. By comparison, in this case, we have 1, 2 methyl hydrogen diaxial interactions, which are 3.8 kilojoules times 2, and 2 hydroxyl hydrogen diaxial interactions, which cost us 2.1 kilojoules times 2, because a hydrogen substituent diaxial interaction is the same energy as a gauche interaction between a methyl group and a substituent. A 1,3 diaxial interaction is the same as a gauche methyl interaction. This in turn gives us 7.6 plus 4.2, or 11.6 kilojoules of strain. So as we can see, the diequatorial conformation is lower in energy. So as you can see, we are able to use a model kit to draw out and showcase the chair flip, and we can use a model kit to better understand, by drawing Newman projections, the gauche interactions and 1,3 diaxial interactions present in each conformation. So that concludes this bonus lecture discussion. discussing using a molecular model kit to draw chair flips.